So in this video about the physical and link layers, I'm going to talk about forward error correction, or FEC. So recall that for a given signal-to-noise ratio and modulation scheme, we can compute what the expected bit error rate is. Now this bit error rate, while it can become very, very small for, say, a very high signal strength, it will never reach zero. There's always a chance that there will be a bit error. So in practice, what this means is that because these bit errors, although uncommon, you expect them to happen, directly turning your link layer bits into bits at the physical layer is very, very inefficient, in that the sparsity of the modulation you need or the speed of the symbols that you need in order to have a very, very low bit error rate so that packet bit errors are uncommon is really, really inefficient. It's going to be very, very far from the Shannon limit. That's not a good way to build a high throughput system. So instead, what you want to do is coding. So coding is a way where you add a little bit of redundancy to the data. In this case, we're talking about the physical layer, but you can do it in all kinds of situations. So you add a little bit of redundancy to make up for these expected uncommon bit errors. And in adding in this little bit of redundancy, its cost is much, much smaller than its benefit. And by doing this, you can greatly, greatly improve your link throughput, because just by adding a little bit of redundancy, all your packets get through as opposed to almost none of your packets get through. And this is true in theory as well as practice. So we talk about coding, we also talk about coding gain, which is the ratio of bits, in this case the link layer, to the bits of the physical layer. Coding gain is more general than that, but within networks usually we're talking about the physical layer and the link layer. So 1/2 code means that we turn one link layer bit into two physical layer bits. So there's one redundant bit for every bit. 3/4 code is we turn 3 link layer bits into 4 bits at the physical layer. And this process is forward error correction. The idea is proactively add some additional redundant data to protract and be able to correct potential errors. And it's called forward error correction because you're doing it proactively, forward. You're saying, look, I don't know if you're going to have any errors, but beforehand, I'm just going to add a bit of redundancy so that you can recover from them. This is nice because you don't need any exchanges. The recipient will be able to just decode the data. It's not going to have to say, oh, there was an error. Can you resend this part? And so it saves you the cost of those kinds of message exchanges. So how do you do this? Well, there's all kinds of coding algorithms out there. There's lots of different ones, all kinds of different trade-offs. Here's just a couple of them. So in this video, I'm going to talk about one in particular, Reed Solomon. So I'm going to talk about Reed Solomon because it turns out, compared to many of these others, it's actually mathematically pretty simple. It's also tremendously commonly used. CDs use Reed Solomon, DVDs, DSL lines, WiMAX, RAID 6 storage arrays. All of these systems, all of these communication storage systems use Reed Solomon. Furthermore, compared to some of these other coding algorithms, Reed Solomon is actually pretty mathematically simple. I'm not going to go into all of the details. The basic concept is simple. Actually designing it so that you can implement it very fast involves a bit more math, which I won't go into, but the basic concept is very simple. The key idea behind Reed Solomon is that if I have a polynomial like here, where I have a parabola, right? So I have some ax squared plus bx plus c, then any polynomial of degree k, where here k equals 2, is uniquely determined by k plus 1 points. So that means is that if I give you 3 xy points, so 3 xy points will uniquely determine for a parabola a, b, and c. So why is this useful? So what I can do is I have some data that I want to encode with Reed Solomon. So I take k chunks of this data. These k chunks become coefficients of a k-1 degree polynomial. So for example, I take 3 chunks of data, and those 3 chunks become a, b, and c, these 3 coefficients. Then what I do is I compute n points along this polynomial, right, where n is greater than or equal to k-1. So it should be -1. Right? So I compute these n points, and that's what I send. I send those points along the polynomial. Now what happens is I'm sending n points, but because the original polynomial is of degree k-1, any of those k points, where k is less than n, would allow you to uniquely and correctly determine what these coefficients were. So for example, I have a second degree polynomial, which I generated from 3 chunks of data, a, b, and c. Then what I do is I compute 0.0, 0.1, 0.2, say 0.3, 0.4, 0.5, and 0.6. And ascend P0, P1, P2, P3, P4, P5, P6. Now it turns out that with any of these 3 points, right, with P1, P5, and P6, or with P4, P1, and P3, you can, if you know this is a parabola, you can determine what A, B, and C are. So that's the basic math. I compute points along a polynomial whose coefficients are the original data. And then if I'm able to recover enough of those points of the polynomial, I can reconstitute what those coefficients were. There's some complications to this, like I can't choose like P2 can't be 1,000,000 because how would I represent 1,000,000? Then it's going to take up more space. And so there's some complications where the actual numbers you use aren't just basic integers. They're things, numbers in a finite field, which means sort of mathematical construct where it's closed over operations. Which essentially means that, hey, I can represent each of these points in a finite number of bits. It's not like suddenly A is 1,000,000, and then that means that P6 is something totally off the charts, and I can't represent it in a finite space. And so that's one of the other complications that I'm not going to go into. But this is the basic idea, is that I represent the data as coefficients of a polynomial. I compute points along the polynomial, then I send those points, and then the other side from those points can reconstitute the coefficients. Now, a little bit more detail in terms of what Reed Solomon can do for you. So it turns out in these kinds of systems, there are 2 kinds of errors we care about, and it's important to distinguish them. The first are erasures. So these are errors where we know that they occurred, like that piece of data is missing. That's an erasure. The other is a general error. We don't know where the error occurred. So this is what we normally think of in terms of, say, bit errors, whereas erased values are, say, oh gosh, this disk didn't answer. Oh, we missed that packet. And so what Reed Solomon does is you're taking k chunks of data and you're coding it into n chunks, where n is greater than or equal to k, where if n is equal to k, you're not actually doing any coding. And what Reed Solomon will do is it can correct up to n minus k erasures, right? Because remember, if we code into n chunks, if we have k points and we know those k points are correct because we're just missing the others, we can reconstitute the data. But it can also correct up to n minus k divided by 2 errors. So let's say we have a very common Reed Solomon code is 223.255, which means that we take 223 bytes of data and turn it into 255 coded bytes of data. Well, 255 minus 223 is equal to 32. So I mean, this particular Reed Solomon code can protect against 32 erasures or 16 errors, where 32 of the 8-bit code words can be missing. As long as we've got 223, we can reconstitute the original data. That's 223 points on our 222-degree polynomial. Or if 16 of them have bit errors in them, we can still reconstitute the original data. So here's that conceptually. Let's take 223 8-bit values. So we take our data, break it into bytes, take 223 bytes. We're going to consider those now the coefficients of a 222-degree polynomial p. We then compute p of 0, p of 1, p of 2, et cetera, as 8-bit values. There's this idea of using a field rather than arbitrary numbers. There's that mathematical concept. So we can then represent them as 8-bit values. We then send these 255 points along the polynomial. And so this is a 255-223 code. Each of these 255 code words come from 223 data words, 32 erasures, 16 errors. So we send these 255 values. And that's the basic idea, is that if I have up to 16 errors, I can still figure out which ones are wrong, and I can reconstitute the polynomial. I can reconstitute the polynomial coefficients, or I could be missing 32 of them. As long as I get 223, if I have 32 erasures, I can still reconstitute the original polynomial. So as I said before, this isn't exactly what's done in practice for a bunch of reasons. These values have to be in a concept called a field. It turns out that this exact scheme is actually pretty expensive to decode. You have to consider all possible parameters and do an interpolation. But it's giving you the basic idea. The more modern ones are a bit more complex, but the basic idea holds of you using the original data as coefficients on a polynomial, computing points along that polynomial, and then sending those points. So here is a simple example. I take these 6 bytes that say hello. I'm breaking them up into chunks of data. I then do my Reed Solomon coding here. is the basic concept, right? I'm adding my forward error correction here, some redundant data. Then when that data arrives, I can decode it and get the original data. So let's walk through this as a specific example. So in this case, let's say we're using a 7.5 code. What this means is that each initial data word that we're going to use is 3 bits long. That's determined by the 7, 2 to the 3 minus 1. So we're breaking the data up into little chunks of 3 bits. And so we're going to start with 5 of these data words, so 15 bits. And each 15 bits are going to be turned into 7 code words. So here we have the first 15 bits, the next 15 bits, the next 15 bits. So it turns out we have 48 bits here. 48 is not evenly divisible by 15. So we have 45 plus 3. So we'll just pad this with zeros. So original data is going to grow from 48 to 60 bits. We then perform the Reed Solomon coding to turn these 15 bits into 21 bits. And then send these total of 84 bits along, say, the wire or on the wireless. Those 84 bits are transmitted, received. The other side gets these 84 coded bits, then runs a Reed Solomon decoder, and from that can regenerate the original data. So since this is a 7.5 code, that means that we can recover from 1 error or 2 erasures. But note that these errors and erasures are for code words. And so it's possible, in fact, that if we have, let's say we have bit errors that look like this. Here's a bit error, here's a bit error, here are 2 bit errors. You can ask the question, will we be able to recover from these bit errors? So for this first code block, the answer is yes, there's a single bit error. A single bit error will corrupt at most 1 code word. We can recover from one code word with an error, and so this first block will be able to successfully recover. The same with the second code block. We have 1 bit error. That means 1 code word will be an error, so we can recover from that. For the third code block, well, this is a tricky question. So one of our code words can be an error, and we have 2 bit errors. So this now depends on where those bit errors fall. If, let's say, here are code words spaced out. Here's 2, 3, 4, 5, 6, 7. Let's say they look like this. Well, if the 2 bit errors are in the same code word, then we'll be okay, because we just have 1 error, 1 code word with an error. So in that case, we'd be all right. However, if the bit errors are in different code words, then we will not be all right, because we'll have 2 errors. We can't recover from 2 errors. So this might not seem very good, but compared to what happens if we were not to use any coding whatsoever, here we've been able to protect against at least 2 bit errors, and maybe even up to 4. So there's one other trick that you can use. This is very common. This, for example, is done in CDs. So one of the assumptions you often have is that errors in the physical layer, some of them are just interspersed and random. Those are easy to handle. What's hard are bursts of errors. And so the way you can make your coding scheme more robust to bursts of errors is through something called interleaving. So imagine, for example, here's my data, and there's 12 chunks of a 7.5 code. So that means that each of these chunks is, in terms of the coded data, is 21 bits long. Remember from the prior showing it's 7 code words that are 3 bits long each. And so here I have 12 code blocks from A to L with bits A0 to A20 and say L0 to L20. So let's think about what happens when we have a burst of errors. So it's possible with, let's say, a burst of 1 error. Well, I know for sure I'm going to be able to recover from that, because that's going to corrupt at most 1 code word in 1 block, and I can recover from 1 error. So that will be okay. 1 bit error. I'm okay. How about 2 bit errors? Well, again, It's going to matter on whether they fall in the same code word or if they say fall on different code words. In fact, it's possible that it could each fall on, I have a burst of 2 errors. One falls on a code word in one block. That block can be recovered. Another falls on a code word in another block. That can be recovered. We would be okay. So in this case, we would be okay. If they both fell within a single code word, we would be okay. But if they fell on 2 different code words within the same block, then we won't be able to recover from that. There'll be 2 errors within a single block. In fact, it turns out if we were to look at what's the longest string of bit errors that we could possibly recover from, that's a good question. So it turns out that the longest that we can recover from is 6-bit errors. And we can recover from a burst of 6-bit errors if and only if it happens to be that 3 of them fall on the last code word of one block, and then 3 fall on the first code word of the next block. Because you can imagine if we add one more, it's going to corrupt the second code word. So that is possible, but unlikely. So this is the longest possible string of errors we could correct from using just a basic coding. So what we can do instead is something called interleaving. So rather than send our data as A0 through A20, B through B20, where then a burst of errors is concentrated on a block, instead what we send is these bits interleaved. For example, we send A0, B0, C0, D0, etc., 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 to L0, A1, B1, C1, ... to L1. Then at the end, we're going to send K20, L20. And so now what happens is that a burst of errors at the physical layer is spread out across all of the different code blocks. So in this case, if we have even a string of 12-bit errors, a string of 12-bit errors is going to cause 1-bit error on every single one of the code blocks. So it'll cause 1-bit error in A, 1-bit error in B, 1-bit error in C, 1-bit error in L. And so in that way, we're suddenly become more robust. So with interleaving, by interleaving all of these bits, we can recover up to 12-bit errors with interleaving. Where even when we didn't have interleaving, even 2-bit errors can cause our system to fail. And 6-bit error is the most we could ever do. But if all we do is interleave these bits, we can deterministically, knowingly, recover a burst up to 12 bits long. So interleaving is a very common and a very popular technique. So this concludes the video on coding. If you want to read more, there's all kinds of interesting coding algorithms out there. I also suggest, if you want, dig into the math of Reed Solomon in terms of how it works in practice to make efficient coding and decoding.